Next, let us do calculations. In order to calculate the reflection and transmission at fixed wavelengths, this one, and at the fixed incident angle, this one, just click here. You can change any parameters, for example incident angle, and recalculate again. This is reflection and transmission for TM or P polarization, and this is reflection and transmission for T or S polarization. This number shows how much light is absorbed in the structure. Since we use all transparent material without metal or absorber, this absorption is 0. Simultaneously, the distribution of optical field across the thickness is calculated. This is for T polarization and this is for TM polarization. Specific parameters of optical field, which is shown on each graph, can be chosen here. It is possible to choose a specific electrical or magnetic field, ellipticity, or phase even here. For example, let's show the still intensity but sweep TTM. So if we for example use T here and TM here, you see. This data is calculated for the case when the light incident is from air, meaning that the refractive index of this first layer equals 1, as you can see here. It's also possible to calculate the case when a prism is used as first layer. Here I input prism angle, like say 60 degree, which is angle between the film plane and prism plane, this angle. Here I input the incident angle. Let's put like a 40. The incident angle is angle between film normal and light incident direction, this angle. Here input the refractive index of prism, for example 2.2. We also can choose as usually any specific material downloaded in usual way. So it will be also, we can see wavelength dependence. So put use. So you can see that when we change incident angle here, for example prism incident angle, this angle, put that 30, you can see it's immediately changed here. So that is angle inside of prism with this refractive index. Or for example if we put 40, you see it's changed accordingly. Similarly, we can calculate the reflection and transmission by clicking here. As I mentioned, we can also set specific material, for example, as well as you do from formula. Let use silicon dioxide, for example, as a prism. So put 0, as I always do. I need only one layer, 0 layers here. So we have a silicon dioxide as a prism. But so now let's set still air. So choose air here. Okay. If we put the refractive index of prism equal 1, meaning the air, the incident angle equals here and in here, for example. If I put 45, 45, 30, 30. Okay, so let's not use prism. And we can push recalculate. Yes, now the last air layer is rather thick 1 micrometer, yes, you see, and it does not have any information. So let's reduce it. And also let's little bit increase incident angle. Next, I will explain how to scan one of the parameters. Here we can choose the parameter to scan. We can choose like incident angle, wavelength, or thickness, refractive index of any of the layers, the multi-layer structure. For example, let us scan the incident angle. So choose incident angle here. Let's scan the incident angle from 0 degree to 85 degree. 0 degree means normal incident, so perpendicular to the interface. 85 degree means the incidence near parallel to the film. Click here to calculate. So this graph shows the data for reflectivity and transmission. The white line shows the data for T or S polarization, and red line shows the data for TM or P polarization. Here we can choose the calculated parameters shown in the graph. We can choose either transmission, reflection, or skin depth, or absorption, or any phase or ellipticity of reflective wave and transmitted wave. Same for this graph, so we can compare. By dragging the cursor in each graph, you see, it is possible to choose the calculated parameters shown in the graph. For example, this means at angle 53.125 degree, reflectivity is 0.42 and something. It is even possible to jump from one line to another, like this. So from one polarization to another. Yes. Scan is calculated. It's possible to animate the field distribution against scan parameters here. For the animation, just push forward or backward buttons here. You see that is a field change as function of parameter. When we click on the forward and backward button, the position of cursor here changes as well. The cursor shows the current incident angle and reflection and transmission. You see cursor change, and this is the field corresponding to this position of cursor, this angle, and corresponding the transmission and reflection. Also, it is useful to plot several field distribution corresponding to different scan parameters on the same graph. For example, let's reduce number of the scan number of calculated points only to 10, and put 10 here, and now let's put still 1, and we're starting from this point, first point. So now let's put 10, and next let's go. So you see 10 points. That is how the field distribution change when the angle is increased from 0 to 85 degree. Okay, so let's return back to one graph. Next, let's scan the wavelengths. You can see the program hints the possible scanning range from this wavelength to some another wavelengths, but let's scan in this range. By the way, so when you change wavelengths, according to the material dispersion, you see refractive index. It changed. We calculate. So let's let's scan wavelengths from 800 to this wavelengths. Yeah, you see reflection and transmission, not so large change. We can push again just to rescale. Well, finally, it is possible to scan the thickness or real or imaginary part of the refractive index of one layer in multilayer structure, or to scan several layers simultaneously. First, let us scan the thickness of this one garnet layer. For this purpose, I'm choosing here thickness of G layer. It means the thickness of layer with number G. Since we're scanning only one layer, for repetition number here, let's input 0. No repetition means. Here, the number of layer we are going to scan. We need to find this number for our garnet layer. For this purpose, let's go here. Yeah. This is garnet. Move it to the left. Yeah, left. So this number, this number is garnet layer number 15. So we put this number here. Okay. You can see immediately, we can see the hint about the thickness of garnet layer 500. You see 500 here. It means we choose correct number. For example, if we input like 16, we can see it's zirconium oxide thickness 7, or 17 silicon oxide thickness here. So correct number is 15 for garnet. In order to calculate, just click here. This is calculated transmission and reflection as function of thickness of garnets from 500 to 1000 nanometers. Additionally, we can check animation how the distribution of optical field changes versus garnet thickness. So just you see the garnet thickness is changing. You can clearly see it. Also, we can check same all distribution on same graph. So 10 points, maybe put 10 here. And we can see how the distribution change when the garnet thickness is changed. Let's put one again. Next, let us scan the thickness of every SiO2 layer in the upper mirror here. It means that we change the thickness of every SiO2 layer simultaneously. You can see that the SiO2 layers each second layer in the mirror. Therefore, we need to input 2 into the repetition number 2. Therefore, once again, 0 for the repetition number means no repetition at all. 2 means the layer is repeated in each second layer. 3 means the layer is repeated in each third layer, and so on. Next, I will find the lowest layers in the mirror. The lowest silicon dioxide layer is just second layer after garnet. See garnet here. Next corium oxide, next silicon oxide. So we should put 17 here. Here's a hint. Yeah, 17. Hint 5. So it started. So the current thickness is 5. So let's scan to 50 nanometers. As always, click here. Yeah, this is calculated reflection, and this is calculated transmission. Again, we can check the animation. You see the thickness of only this layer is changing in upper mirror. Yes, from smaller getting thicker and thicker as shown here. Just now we have scanned the thickness of every SiO2 layer in the upper mirror. Next, I want to scan the thickness of every silicon dioxide layer in both the upper and lower mirrors. I cannot use the same periodical scan in this case, because periodicity is broken in this case due to the middle garnet layer. For example, if I would use the periodicity 2 starting from the lower mirror, the logic will be broken after the garnet. For this purpose, it's necessary to use another available option, which is scan by name. In this case, scan all layers with the same name as scanned. So I come back to program and choose the thickness of the same name. As a starting layer, we could choose any layer with the name silicon dioxide. For example, layer 17 is okay. On layer 6 is okay. So let's input like 6. Any name, any layer with this name is okay. And again we have a hint of 5 here. So let's scan again till 50 nanometers or 60 nanometers. As always, click here. Okay. This is calculated reflection, this is calculated transmission. Again, we can check the animation. You see the thickness of SiO2 layer changed in both lower and upper mirrors. In a case, if I like to scan all silicon dioxide layers, but with some exception, for example, 1 or 2 specific layers we do not want to scan. It's like a defect or something in this periodical 1D crystal. For this purpose, I need to change the name of these specific layers. For example, let's choose like a layer number 2, we put just B here, in lower layer, and maybe in upper layer also you put B, or you can put C or anything. And push the scan. And you can see there's 2 layers which thickness does not change. One layer in lower mirror, and one layer in upper mirror. So let's change back this layers. I think we change like an layer here. The next case is when I want to scan the thickness of all silicon dioxide layers in lower mirror, but without scanning of silicon dioxide in the upper mirror. For this purpose, I need to change all silicon dioxide names in the upper mirror that it should be different from silicon oxide names in the lower mirror, so it will scan only in lower mirror. Easy way to rename many layers is just re-input them. So put here, let's take silicon dioxide from formula. Put some B or C or 2, for example, 2 here. Silicon dioxide thickness is 5. And we need to input it after periodicity is 2, yes, it's second layer. And we need just input after garnet. So that is garnet, first layer is is garnet 15, 17, yes. Yeah, 15, 16, 17. So started from 17. And periodicity to set layer, thickness 5. So you see here all renamed with 2, but here still remain without 2. Push set layer. And we scan lower, the 6 should be correspond to lower layers, still in lower. 6, select again, start from 5 to 60 nanometers. Push calculate scan. And you see only this in lower thickness in lower mirror changing, but without changing upper mirror. Upper mirror remain constant. In this part, we just have calculated all parameters of reflection and transmission for TE or S polarization and TM or P polarization. This part calculates the reflection and transmission for any arbitrary polarization, for example, a circular or elliptical polarization, and how such a polarization is transformed after the reflection and transmission. Here, we can choose any polarization of incident light. Here, we can choose the ratio between the S and P component of the polarization. An angle of rotation between its S and P polarization is used for this purpose. 0 degree means only S polarization. 90 degree means only the P polarization. And 45 degrees means the equal amplitude of S and P polarization. This is the phase between P and S polarization. 0 degree means that P and S polarization is in the phase and incident polarization is linear. Phase 90 degree and equal P and S polarizations mean the incident light is circularly polarized. In order to calculate, click here. This is calculated polarization of reflected and transmitted light. Again, this is a ratio is between S and P polarization components, and this is phase between them. Yeah, so you can change, for example, also 45. You see, there's a change. If you like to change either incident angle or wavelengths, you need to click here to recalculate whole stuff. Let's put 45. Additionally, it is possible to scan the polarization of incident light and calculate how this polarization of reflected transmitted light changes versus incident polarization. This part you can do here. For example, let us scan the phase between PS polarization. So choose here phase. In case when the amplitude of PS components are equal, so 45 is here. It means that scan from left circularly polarized to linearly polarized and to right circularly polarized light. We can calculate many different parameters which can be chosen here. Let us calculate the ellipticity of reflected light. Click here. That is a calculated dependence. can compare it with the case of different incident angles. So let's increase number of graph to 2. Let's choose another angle like 70 degree. Let's push calculate and push here again. So white line shows here for this 70 degree incident angle, and red line showed previous data for 40 degree incident angle. I have finished explanation about calculations. Next I will explain some small tips. It's rather easy to copy any graph in LabVIEW. Right click on the graph, for example this, and choose export. Not copy data, but export data to clipboard. Next, go to the origin or any other plotting software which you used and paste the data. Now you can plot it. So it's an identical graph to this. In case of multi-plot graph, you do the same. Export to clipboard, going here and copy. So copy two data. You assign this data to X. Okay. And you plot them. The graph is identical to this one. Another option to save the graph is to click on the Save button, which exists for any graph. Data file is text format is saved in directory My Data. For example, I just name it My Data. My Data. Or you can distribution 2. Additionally, it is possible to load and add your own graph to calculated graph. It is useful when it's necessary to compare the experimental and calculated data. So for simplicity, I just show only one graph. As experimental data, a simple text file should be used, where the first column is the x-axis and second column is y-axis. So for this purpose, I just, for example, copy data of this graph. So let's say it's my experimental data. I go to some directory, for example, my data, and create a new text document, and I name it experiment. For example, data and copy, say experimental data to there and save. Next, just push add experimental data, small dot here. So go to directory My Data and choose experimental data, just file we just created. And you see in white it shows this experimental data, just exactly like this red curve. So this data, experimental data, which can be any. I hope it will be easy for you to use this program. In the case if you have question or you find some bug, please contact me or leave a comment. I hope this program will be useful for you. Thank you.